This is part 2 of the talk on GPU acceleration, and in this part we'll be covering cuDIPY. cuDIPY is basically a subset of DIPY implemented on the GPU. It's a fairly small subset at the moment, but has a number of interesting functions such as for tissue segmentation and non-rigid registration. The implementations are based on cuPy as covered in the previous part, and they range from simple in terms of mostly just swapping out the names of NumPy functions for their cuPy equivalent, or somewhat more complex in terms of having to implement a number of custom element-wise CUDA kernels, but none of them are involve any substantial amount of C++ code. So to install cuDIPY is still a little bit in the experimental phase in that it's not integrated in with the main DIPY project, and it's not yet up on PyPy. So we have to install it from the source repository. I'm going to give examples of how to do that here in Conda, but you could use virtualenv or npip purely if that's what you're used to working with. But for Conda, if you don't already have it, you can download a more minimal version that doesn't include so many packages not relevant to this presentation, and the mini Conda installer, which is basically Python with a few basic things. So once you have that, you'll have access to this conda command once you've installed miniconda or anaconda, and you can use conda env create with this provided cuDIPY environment.yaml file, which will install numpy, DIPY, and other dependencies, and you then activate that as follows. So once you have that environment set up, we want to install cuPy as well, but we don't want to use the default version that this package makes use of functions that have been implemented in cuPy 9, which is pending a final release in April of this year. So right now it's in a separate channel on CondaForge called a release candidate label is applied to it. So we have to specifically request that if we wanted to find a recent version. So once we have cuPy, I do not believe you have to actually have the full CUDA toolkit from NVIDIA. You will have to have the NVIDIA drivers installed for your GPU, but I don't think you need the full CUDA toolkit if you're using this conda package. And then for the cuDIPY project itself, the installation is very simple. It will run pretty instantaneously because it's just a basic Python package, so you can pip install from the URL to the repository. And there's an optional dependency on the cuPy image package I created that has some of the scikit image functions on the GPU. That's the one I mentioned previously will be moving under the Rapids organization in April of this year. So there are a handful of the demos I ported over from DIPY to cuDIPY, so those exist in an equivalent location where if you clone the main repository using git, if you navigate into the subfolder with the examples, you can just run any of those examples from the command line and they'll pop up the figures the same way it works for DIPY itself. I just want to note that on the GPU version, the very first time you run a given example, it will be relatively slow because there's typically dozens of CUDA kernels that it has to compile the first time it sees each one, and then any subsequent times you run that script, it will run much more quickly. So just to look at a few of the things that were implemented so far. One is the basic brain extraction, which is pretty much smoothing with a median filter to remove some noise, and then using this Otsu's method for thresholding, determining foreground versus background, and that on these diffusion weighted images can nicely separate out the brain from the background. And so that's an example of one that's very simple to convert because it's mostly relying on functions from SciPy like binary dilation and median filter, and those functions have already been implemented within cuPy itself, so we can just call their equivalents from there. And so that's kind of a best case scenario in terms of the ease of converting things. And on the radius 4 on the median kernel here. The acceleration factor in GPU is about 10 relative to the CPU version I was running, but with a little bit smaller radius, the GPU actually does a lot better relative to the CPU. A second example is the Gibbs artifact correction, which is basically the ringing that occurs in the spatial domain due to truncation in the Fourier domain. And there's an algorithm for removing that implemented in DIPY that relies, the majority of the computation is done in FFTs. So this one, you know, those FFTs also exist already in cuPy. So we could do a straightforward conversion as in the prior example, except in this case that didn't really give good performance. And it turns out the reason for that is when these are being, there's a loop in the code that runs slice by slice, and each individual slice is typically pretty small, maybe something like 128 by 128 in a kind of diffusion imaging experiment. So those are pretty small FFTs, and there's quite a bit of overhead from so many kernel calls in the GPU. And if we make some minor refactoring of that function, so basically call FFT on the whole batch of slices at once, then we can do quite a bit better. And that ends up getting us to a point where actually if we were to look at the original DIPY 1.2 implementation, at that time it was taking almost 2 minutes to run this function. There were a number of PRs for DIPY 1.3 that improved the performance both in terms of being able to run slices in separate threads, so it's now multi-threaded, and some other efficiency improvements. So it actually is now quite efficient on the CPU side, coming in at only about 5 seconds in DIPY 1.4. But the GPU version is still even faster than that, coming in at 2 seconds in this case on a somewhat old GPU. So these next two examples show a more substantial speed up, but they're also a little bit more involved in the implementation. The next is the tissue classification method. So this is similar to what's being done in the FAST tool from FSL, where you basically want to classify voxels as gray matter, white matter, or CSF, and each voxel will kind of have a percentage of kind of the confidence that they're in one of those categories. So this function relied on some Python code, so it wasn't a pure Python function, and that there's no real way to just port Python to the GPU magically. So basically we have to re-implement an equivalent of those Python functions as CUDA kernels. And it turned out that those end up being things that you can do with element-wise kernels, and they're reasonably straightforward, but it does take a decent amount of work testing and getting that implemented. One other note on the GPU implementation here is that I reused some of the neighborhood operation code that's used in kind of the convolutions in cuPy's ND image implementations, which are n-dimensional. So although the Python code was specific to 3D, the GPU code actually works for 2D, 3D, or I guess potentially more dimensions, although I don't know if there's real-world use cases for those. And this function reduced in time from around 2 minutes to about 2 seconds. So in this case, we got about a 50-fold speed up on the GPU. The last case I'm going to look at in DIPY is a non-rigid registration using the SEN algorithm. This is an algorithm that was popularized in the ANTS library, in which DIPY contains a Python and Python implementation of. This one was the most work out of the ones that were implemented, just because there were a lot of separate Python code used for this to do interpolation, cross-correlation, and various vector field operations. The interpolation part was mostly able to be done using the map coordinates function, which is a SciPy equivalent implemented in cuPy, but the rest of those require element-wise kernels again. So we'll show an example of what one of those looks like in a minute. And then the actual Python side code is very minimal changes to these. They're pretty much the same function, maybe swapping NumPy to cuPy in a couple places, but otherwise not much to do there. So an example of an element-wise kernel declaration is shown here, where this is a kernel that would take in arrays containing x, y, and z coordinates and some matrix containing an affine transform, 4x4 matrix in this case, and the outputs are x, y, and z coordinates again in the transform space. And so the inner loop function for this kernel is basically a 4x4 matrix multiplication. So you're multiplying by these elements by the x, y, and z coordinate, and then adding this offset element. And so there's various kind of small element-wise kernels like this that were implemented in order to get the full functionality needed for the various operations used in this optimization. So I did a little bit of a comparison to another library available in Python that has a GPU implementation. It's called Deformetrica, and it implements another non-rigid algorithm called large deformation diffeomorphic metric mapping, and it's using PyTorch as kind of the underlying library here rather than cuDIPY. So I took the example provided with Deformetrica using their default settings, and then ran that same data through the DIPY as well as the cuDIPY versions, and I just chose a tolerance of e to the -4 in terms of terminating the iterations, which in practice ended up being somewhere at 15 to 25 iterations per resolution level. And the GPU implementation in Deformetrica took a little over a minute to run on their example case. When I ran that on DIPY on the CPU, it took about 9 minutes, and on the GPU about 15 seconds. So we saw acceleration of 35 versus the DIPY CPU implementation, and it was also 5 times faster than the Deformetrica GPU implementation. And I should mention that once you have the warp field, actually applying that field is much faster on the GPU. I mean, up to 100 times or so faster for GPU versus CPU. And we can do the warps in a higher order interpolation as well. So, just show a little bit of what the output of that looks like. This is the input images before registration. So we have a static volume and a moving volume, and we're trying to warp the moving to the static. So if we overlay those at the starting point before any optimization, we can see yellow is kind of where there's overlap, and red and green are indicating where there's intensity in one image but not the other. So the fact that this isn't all yellow is showing there's not great correspondence at the starting point. If you run this through Deformetrica, they're showing example coronal slice on the top, or for DIPY is showing example slice on the bottom. Both of these improve the overlap a lot. We can see some strange looking sections, especially in the LDDM. Looks like some little bit weird sharp looking features that don't look very anatomically plausible to me. It's a little more apparent even on this axial slice here. But okay, so for future work, there's always additional functions we'd like to implement. One I would like to see is kind of so this showed the non-rigid stage, but I haven't converted the linear registration portion over to the GPU. So kind of the normalized mutual information metric and the functions used for that linear case would be a good complement. So we normally want to do some initial linear affine alignment prior to applying the non-rigid registration. There's a number of other functions in DIPY denoise that should be fairly straightforward to convert to the GPU. Another area we talked about but I haven't had a chance to look at much yet is accelerating some of the convex optimizations that get used in the reconstruction models. And we would like to be able to select to use GPUs in kind of some of the DIPY workflow code. Some additional things to think about are how do we want to integrate this GPU backend into the bigger project? And that's something I'm kind of looking at for scikit image right now with the grant through CZI of how we can support doing things with GPU and Dask arrays, and ideally we would like to have kind of a common code base with common code path for GPU and CPU where possible, and maybe just the Cython portion versus CUDA kernels for kind of the core computational bottlenecks where we'd have to have duplicate implementations. And then in general, getting continuous integration up and running on the GPU is a little more challenging since the free CI services don't offer a GPU hardware. So that so yeah, I think that's mostly what I wanted to cover in part 2. I want to mention, for those that are interested, I provided some links here to some NumPy enhancement proposals. These have to do with ways that NumPy itself can dispatch to other array types, so how it can operate. You know, you pass in a PyTorch array or you pass in a cuPy array, and how will NumPy handle that? How can we make it easier for downstream libraries to be able to operate on a range of array types that follow kind of the NumPy API. And so there's a number of ongoing things. These first 3 have already have an implementation in NumPy, and there are some others that have been under discussion.